Sai Ram to all of you. Welcome to this study of coordination compounds, where we will deal with the crystal field theory in this case, because we happen to study valence bond theory, and finally at the end of the theory we realized there were some limitations for that theory. So, the moment any theory has limitations, we need to have further study of the compounds and see how best we can explain that. So, before we go into the study of crystal field theory, let us see the answers for some of the questions that were given in the previous segment. So, the first question, draw the structure of cisplatin. Now, cisplatin is something that is used in chemotherapy, and the structure is having a platinum as the central metal ion, and 4 ligands are present where 2 are chlorine and 2 are amines. The name IUPAC name can be diamine dichlorido platinum 2, because chlorine is negatively charged, there are 2 chlorines, and amine which is there is neutral. So, this is how you can draw the structure of cisplatin. Second one, explain linkage isomerism with a suitable example. As we had discussed it, in this type of isomerism, the molecular formula is same, but what differs is the atom of the ligand which is attacking the central metal ion. So, in the examples that you are seeing here, NH3 is a common ligand for both, but in the other ligand it is the nitrogen of NO2 which attaches to cobalt, whereas in the second example it is the oxygen of the NO2 which attaches to the cobalt. So, this is how you can give suitable examples for the linkage isomerism. Third one, explain the hybridization and magnetic properties of NiCN4 2-. Nickel atomic number is 28. The oxidation state of nickel here is +2, and that is why you get it in 3D8 form. And the 2 unpaired electrons which were there in Ni2+, they are forced to pair because Cn is considered as a strong ligand. And because it is a strong ligand, it was forced to pair, and the leftover orbitals were taken for hybridization, which is dsp2 hybridization. So, magnetic properties, this is going to be diamagnetic because nowhere you are able to see the presence of unpaired electrons. Presence of unpaired electrons only can give you certain magnetic properties. And the fourth and last question, mention any 2 limitations of VBT. You were asked just 2 limitations, but I have put up 4 here just for certain additional points. Doesn't give quantitative interpretation of magnetic data, that is because it tells whether it is magnetic or non-magnetic, but does not give a perfect explanation. No thoughts about color in this valence bond theory, no thoughts about the stabilities, and we only assumed some as strong ligands and some as weak ligands. We did not distinguish it perfectly. So, having seen all these answers, now let us go into a new theory, which is crystal field theory. So, what is this crystal field theory? Let us first see certain basics of this part. This is the presence of d orbitals which is present. This is something that you have studied in the first year structure of atom. You had studied those parts where, suppose if I consider this as x axis, this as y, and this as z axis. Now, when I consider such a system, if I write dxy orbital, what does dxy indicate is that the orbitals are between x and y. It may be on z, but the presence of orbitals should be shown something like this, anywhere between x and y. Similarly, when I consider another type of this orbital presentation, say dyz, if I consider this as x axis, y axis, z axis, what does this mean is, these orbitals should be between y and z. It can be on x, but should not be on x in the y and z form. So, all these things are already studied in structure of atom. You may have studied it in detail, or maybe you must have just studied it from exam point of view. But understanding the presence of these orbitals is very important to study the crystal field theory. So, what do we understand by this is, these type of orbitals, suppose along with this, let me give off the other example also which was there, that is dxz, where if I consider this as y, x, y, z, the orbitals can be between x and z. It can be on y. This is how we wrote these three orbitals. But then there were another two types of orbitals also. Which were those other two type of orbitals? It was named as dx square minus y square. Now what is this dx square minus y square? It means that it is on the axis. Be clear about this. dxy means it is in between the axis, whereas dx square minus y square is on the x axis and on the y axis. What about dz square, which was the fifth orbital that was studied in this case? X, y, z. The naming I am going to do it as dz square. This indicates that both the orbitals are on z axis itself, and what we do here for this is the overlap of orbitals on the z axis is shown with a smaller spherical form which is present here. So this is this one, dx square minus y square, dyz, dz square, dxz. Why am I stressing a lot on this is the exact position of these orbitals are very important to study how the complex compounds are formed. So having understood this part now, we have to understand how do these ligands and central metal ion act between themselves. For example, this central part which is there is nothing but presence of central metal ion in this case. The origin of all these axis systems is considered as M. We know very well that generally if you want to write say Ml6, which is for octahedral system, M is the central metal ion, L is the ligand system which is there. So in these cases now, what is important to be understood is the origin is the central metal ion and the axis here indicate the presence of ligand. For example, let me take the first study of dxy. What does this system indicate is there are ligands present on all the axes that are shown here. Let me repeat it. Ligands are shown on all the axes. So in total there are 6 ligands which are shown, and orbitals are shown like this. Now what do ligands do? What is the role of ligands? We have studied that they donate a pair of electrons. That is why we show coordinate bond like this. What does this indicate is they donate a pair of electrons to the system. So understand here, ligand is donating a pair of electrons to the central metal ion. The orbitals of this metal are not on the axis, they are in between the axis. So once again, electrons are given by ligand, electrons of this metal are present in the orbital. That is what the definition of orbital we have studied, the 3-dimensional representation of the presence of electrons. So here what we understand is electrons are coming here, ligand electrons are coming here, but the electron orbitals of metal is present in between the axis, which means that the repulsion between these two electrons is comparatively less, and lesser repulsion indicates more stability to the compound. So which indicates that dxy is pretty stable. Even here also, when I try to replace these parts as ligands, L, L, all the 6 1, let me write it as ligands. What I understand here is that ligand will give electrons along the axis, on the axis, but orbitals are present in between the axis. So the electrons of metal and electrons of ligand are a little far away, so the repulsion is less. Always remember, like charges repel. So electron naturally repulsion will be there, but here it is comparatively less because of the separation. Similarly in this case, so what I can show here is all the 6 axes, let me show them as ligand, and these 6 ligands are donating electrons to the central metal ion, and the orbitals of central metal ion are present in between the axis. But now come here, when you come on dx square minus y square, the ligand position remains the same, which is nothing but on the axis. So ligands are giving electrons on the axis, the orbitals of metal is also on the axis, means the electrons of ligand and electrons of the metal are present on the same axis, which means they are actually colliding each other, and the presence of electrons together actually leads to repulsion. So we can understand that this condition will have high repulsion in place. Now what does high repulsion indicate? If repulsion is more, there can't be stability. If you have some repulsion with your friends, do you think your relationship is stable? Definitely not. So when there is good amount of repulsion available here, the stability of the compound is decreased. So when I compare these two, the stability of dxy, dyz, dxz is a little more, but dx square minus y square is less. What about dz square now then? No doubt ligands, when I write it, I am going to show it up like this, that the 6 ligands are present on the axis. Good thing is there is no orbitals of metal on x axis as well as y axis. But what is the problem with z axis? Z axis actually has 2 ligands. If you see here, it has 2 ligands, and both the orbitals of this metal are present on Z itself, which means maximum repulsion is shown in this case, and that is why the overall repulsion possibility of this dz square is also less. This is one basic important part for this crystal field theory. To understand that, d orbitals, no doubt everybody will have same. So same energy levels, we call them as degenerate orbitals. For example, yes, there is only one type, 1s, 2s, 3s, 4s, all these basics you have studied in periodic classification. Whereas P has 3 types of orbitals. If you remember, we had P as a Px, Py and Pz. But all these 3 have same energy level. Always remember, you are going to apply Hund's rule, Aufbau principle whenever you are filling electrons. And how do you fill electrons? You first fill here 1, 2, 3 and then you pair it up, because all these 3 are in the same energy level. Similarly, we believed that D, which has 5 different types, are in same energy level. But if there are ligands attacking, the original metal will have 5 d orbitals and all of them will be in the same. In the presence of attack of ligands, we are able to see that the repulsions in these cases are less, in these cases are more, which means that there will not be degeneracy available. These two also will split up much further because the energy levels are different for this case. You will not have any such thing for p orbitals. So I hope you have understood the entire structural aspect of the interaction of metal and ligand. So having understood this basic aspects of the interactions, let us now see some postulates of crystal field theory which is present. So in the postulate parts now, let us see those there. In this, the crystal field theory is an electrostatic model. Electro indicates that there is play of electrons here, and it is static, means that the compound is already formed. The crystal field theory is an electrostatic model which considers metal ligand bond to be ionic, arising purely from electrostatic interactions between the metal ion and ligand. That is what was explained here by me, that in the cases of these parts, the interactions between metal and the ligand is what determines this crystal field theory. This was the first point of the postulate. Let us see the second point now of the postulate. Ligands are treated as point charges in the case of anions. What does this mean is, these ligands are something which are in interaction with the metal, and this is one point, one point, one point, one point, one point, like this. Every single parts of this are individual point particles which are interacting with the central metal ion. The third point here says that ligands are treated as dipoles in the case of neutral molecules. Now these neutral molecules, which are the examples of neutral molecules we have seen? We have seen NH3 which has lone pair of electron, we have seen water which has lone pair of electron, which means that they do not have charges, and that is why they are present as dipole. Now what do you mean by dipole? Di, two. Pole means something which are apart. So those as dipole can attack to the central metal ion as ligands. Fourth point in this crystal field theory, the 5 d orbitals in an isolated gaseous metal atom have same energy. That is what I mean to say, that when it is just as a metal, all these 5 are same. All the 5 orbitals, dxy, dyz, dzx, dx square minus y square, dz square, all the 5 are in the same energy level. When do they create a problem? It is only when ligands comes and attack, and then we see the repulsions in these two sets. That is when they try to split up. That is what is the next point you can see there, that This degeneracy basically means having same energy. When the 5 d orbitals were there, they were degenerate. This degeneracy is maintained if a spherically symmetrical field of negative charges surround the central metal ion, which means that if there are ligands which are not symmetrical as such, they can come and disturb this sort of energy dimensions which are there. Seeing the further points of this, we can see when the negative field is due to ligands, it becomes asymmetrical and the degeneracy of d orbital is lifted. Here lifted indicates that all the 5 d orbitals which were in the straight same energy level are now not so, and they are split into different types, and that pattern of splitting, it depends on the nature of crystal field. If the ligands are very strong, the splitting will be very high. It means that the gap between the two will be very high. If the ligands are weak, the gap will also be comparatively less. So what is the actual pictorial representation of this? This is the one. See towards the one side, you have energy on the y-axis. You have all the 5 orbitals which are written in one single line, which means that all of them have same energy. Dx square minus y square, dz square, dxy, dyz, dzx. And see what is written down, free metal ion, means that there is only metal present. Now when the ligand has attacked, what has happened? All these d orbitals have risen in their energy. Always remember, higher energy indicates lower stability, and in this case you are able to see that dxy, yz and zx are kept lower, and x square minus y square and dz square are kept higher. Now why is it that they are kept higher? Let me just repeat the point. These two orbitals are higher because metal orbitals and ligand electrons are along the axis, so repulsion is high. Same thing here, ligand electrons and metal orbitals are on the axis, but in these cases ligands are on the axis, these metallic forms which are there, they are in between the axis, so repulsion is less. Less repulsion, more stability will have lesser energy. Always this is the factor which we know, that high stable compounds will have stable energy or lesser energy in them. So this is the pictorial representation that we have for the octahedral entities. And what is delta naught? If you are able to see there, 3 by 5 delta naught, 2 by 5 delta naught. What is that is? Delta naught is splitting in octahedral systems. It indicates how much energy is being split into. And 2 by 5, 3 by 5 is because if you have to give high energy, you need more energy for the system. That is why only the 2 orbitals dx square minus y square and dz square have up to 3 by 5, which means that of the 5 parts, 3 parts of energy are required for these 2 orbitals. That is why they have high energy. Whereas 2 parts of the energy of this d orbitals is required for stability of dxy, dxz and dyz. So what is now important in this understanding is that once we get these type of orbital systems, the question now arises, how will you fill the electrons in this system? Remember that whenever we have to give stability to the compounds, it indicates that the stability factors only come through whenever there is a splitting of electron system. So let me show certain splittings that have happened. So all the d orbitals were present as it is. After ligand came and attacked, this is what happened. So dx square minus y square went above, dz square also went above. So why they have gone up, why they have gone down, that is already discussed for now. Now the question is, how will you fill the electrons? Now when the first electron comes there from the ligand, or say from the central metal ion, the first electron of the central metal ion, when it is only d, you can write in any one, dxy, dyz, dzx, or dx square minus y square, dz square, any one you can write. But here we have to follow the rules where lower energy systems have to be filled first and then higher energy system. So the first electron will naturally come here. This is actually named as T2G level, this is named as EG level. What are these? These actually come at a much later higher steady states, like say postgraduate level or so, where these are called as symmetric point molecules. This study is not needed for you. I think as of now, if you know that this is 2,2G and this is EG, that should be more than enough. So the first electron will go here because this is of lesser energy. The second electron naturally will go here, third electron will go here. We know by the rules that first you have to play it individually. Now the question is, what about the fourth electron? Should it come here and pair, or should it go above and then put up a single electron? So in general cases, what you used to do when you used to fill that 1s, 2p, 2s, 2p, 3s, 3p, all those things, you would first fill the energy which is down and then go for up. But here, because it is the same orbital, the difference in this energy matters for this case. The difference I have shown it as delta naught, and then I am going to introduce another factor called as pairing energy, is denoted by P. Now what do you define pairing energy as? Pairing energy is that energy which is required to pair the electrons when the fourth electron comes and attacks. And not just fourth electron, in this case I am discussing about fourth electron. Any electron when it comes and pairs, the energy required for that is pairing energy. And what is delta naught? It is the energy difference in this case. So it depends on the energy required for pairing and delta naught to determine whether the next electron will go here or whether the next electron will come here. So what are those factors that let us see in this cases here? You will see that if delta naught is less than P, what does this indicate now? This delta naught system which is there, they are saying that this energy required is much lesser than pairing energy. So if you go for pairing, you will need high energy. See, any work you do, you will try to do it with minimum energy. You are not going to exert a lot of energy. Whichever routes are possible, the best chosen route is always that which involves minimum energy. So if the case is such that, suppose let me consider this as case 1, if the case is such that this is having lesser energy, then the fourth electron will come here. When I write the configuration for this, I am actually going to write it as T2G3 Eg1 because this energy was pretty less. So my fourth electron I went and added here. This is one case. Suppose in the second case now, where delta naught is actually greater than P. What does this mean? The pairing energy is actually pretty less, and this delta naught, which is the difference between these two, is very high. Then it means that it rather prefers pairing because that energy required is less. And in that case, what happens? The fourth electron, instead of going here, will rather try to pair here first. And what will be this configuration then? It will be T2G4Eg0. So this is how the difference in energy will determine where the electrons will go, and the transfer of these electrons we call it as a d-d transition because this is also a d orbital, this is also d orbital. So the transition between these two we can call them as d orbitals. So let us just revise these parts whatever I told. If you see it here, if delta naught is less than P, the fourth electron enters one of the Eg orbitals. Why it has entered Eg orbitals? It is because these systems which are there, they are able to have this as a lesser energy system, and these are generally, if they go up, we generally call them as weak ligands. Weak ligands because the splitting, the ligand which actually came and attacked, see originally the metal was having only d orbitals. When did this splitting happen? Only when ligand came and attached. So if it is a weak ligand, it will not have so much splitting. So generally this type of filling is supported by weak ligands because they are not able to split more. Now who can split 2 very high? It is being split by strong ligand. So if there is strong ligand, the fourth electron will not go here, the fourth electron will rather put up here. So strong ligands will support pairing, weak ligands will rather support usage of both these orbitals. So if you see the second point in the case where they are given, if delta naught is greater than P, then it becomes more energetically favorable for the fourth electron to rather have a pairing system in their cases. Now that pairing is possible because the splitting caused by strong ligands is very high, and therefore it rather goes for pairing in those compounds. So in this, as a case study, let me just give you certain differences which are possible in this case, where a correlative study for weak ligand and strong ligand, that let us study. So in this cases now, we can see that one side I will be showing regarding the weak ligand, how it processes. The other side I will be showing regarding the strong ligand, how it processes. So, in this case, let me say that this part which is there is the weak ligand section, and this part which is there is the strong ligand section. So, what differences will be possible here? Let us see. If it is a strong ligand, be clear that this will be very high. If it is a weak ligand, this will be pretty much less. So, I am just showing it pictorially how the splitting can take place. And the central D that I have written is basically for central metal ion which is present without the attack of ligands. So, when the ligands have attached here, if it is in the case of strong ligand, 1, 2, 3 will happen. Even in the case of weak ligand, first electron, second electron, third electron. What about fourth electron now? If it is a strong ligand, splitting is too high. So, therefore, what it does, it rather goes to pair. If it is a weak ligand, the splitting is very small, so it would rather go and occupy at the top. This is the case study of fourth ligand, fourth electron. What about fifth electron now? The fifth electron will pair here if it is a strong ligand, because the pairing has started, whereas the fifth electron here will reach here. What about sixth one now? Sixth one will pair this. In this case, since all the 5 are individually filled, the sixth electron will hold up here. Seventh one will come here, because all the down parts are now filled, you have to go up, whereas here seventh one will fill this. Eighth electron will come here, because these two are in same energy level now. So, that is why you can't pair this. First you have to make it individually occupied. Eighth electron will come here. Now, what you can see is that by the end of 8th electron, actually both of them have become same. Here also it is 6 plus 2, here also it is 6 plus 2. What about the 9th electron? 9th will come here, 9th will come here, 10th will come here, 10th will come here. So, this is how we can analyze that the difference only comes for D4 system, D5 system, D6 system, D7 system. It does not come for any other cases at all. So, this is how the splitting of this system are been shown in these cases. Now, having seen this type of differences that are present, let us see other set of orbitals which is nothing but tetrahedral orbitals. And for tetrahedral entities, the moment you see the diagram now, the whole picture has been reversed. All this while in octahedral we used to tell that dxy, dyz, dzx has lesser repulsion, and that is why they are more stable, and dx square minus y square dz square were written high, but you are able to see an exact opposite of the tetrahedral systems which are present. Now, this is so because for this you need to understand what is the structure of this tetrahedral molecule. We have studied many a times CH4 in organic chemistry, that has formed basis that the CH4 molecule is tetrahedral in nature. On a 2-dimensional paper we write it like this, where the angle between these two is 109 degree 28 minutes. This is something that you have studied in organic chemistry. Now, how are the axes of orbitals present? See, always axes will be present 90 degree to each other. This is x axis, this is y axis, this is z axis. They will be 90 to each other. Even though you are able to see z axis in between, so this you have to analyze it in the 3-dimensional space that. So, in the 3-dimension system, if this is a formation of an x and y, the z axis is actually towards this plane. So, in this case now they are all 90 degree to each other, but here it is not 90 degree, it is 109 degree 28 minutes, which means that the orbitals, the ligands which are there in octahedral cases, you realize that ligands are always on the axis. You had written L in these places if you remember, but now you can't write L in these places in the case of tetrahedral, because they are not 90 degrees to each other, they are 109 degree 28 minutes to each other, where the concept becomes reverse now. dxy actually has metal orbitals in between the axis, ligands are also in between the axis, because the degree is 109 degree 28 minutes. Whereas dx square minus y square, the metal orbitals are on the axis, but ligands are in between the axis. So, therefore, the repulsion cases change, and if you see the diagrammatic way of the tetrahedral system, you are able to see that dxy, dyz, dzx have come on the top, and dx square minus y square and dz square are down. So, same explanatory parts for the tetrahedral systems also, like octahedral parts. So moving on, color in this coordination compound. So in VBT they did not discuss anything regarding color, whereas now they are going to discuss here regarding the color, and that they were attributed to DD transition. So what is that DD transition is? These electron systems which are there, if they are present in lower orbital forms, they are able to go to higher energy level, and we know that color is exhibited whenever they come back from higher system to lower system. Now suppose in this case you had one electron. If you supply energy to this, there is only one electron, and if you supply energy to this, it will go to the higher energy state because you have supplied energy. So this electron which is there will go up here only when you supply energy. Once the supply of energy is removed, it has to come back, and while coming back it will give out some energy in the form of light. So here the color of the coordination compounds are being explained to you, unlike VBT, where the color of the compound is explained with respect to DD transition, because this is also d orbital, this is also d orbital. So when you supply energy, electron from lower energy goes to higher energy. Once the supply is removed, it can't stay there because it doesn't have any more energy, so it tries to come back, and while this electron comes back, it gives out energy, and that energy is given out in the form of light. So let us see some color properties of this coordination compounds here, where you can see some of the compounds are different properties of color, and we have studied this in D block elements and all that. The color of the compound is actually the one which is the complementary color of the absorbed radiation. This was studied in D block elements while studying the color of compounds, where supposing if the color of the absorbed light is yellow, the color that you can actually see is violet, because these two colors are complementary. You can see the complementary colorations there. Blue green converts to red. If you absorb blue color, then it becomes yellow orange color. Now all this color of these compounds are something which are checked out practically for the compounds that are given there. You are being given around 6 compounds, and the color of this is explained to the DD transitions that happen in these compounds. Similarly, whenever we want to form complex compounds like aqua compounds of nickel, this same nickel which is there, you are able to see that with the change in the ligands that are present, it does affect the overall coloration of the compound, because different ligands will absorb various wavelengths of light. And we know that from 400 nanometer to 800 nanometer, the visible range of light is seen, and whatever they absorb, they will give out the complementary color. So if you see here, all the 3 sets of compounds which are shown in the reaction example, and also 4 set of colored compounds that are shown, you are able to see a change in color from green, blue, violet to pinkish of sorts. Now that is because as you go from one side to the other, the aqua molecules in the complex is coming down from 6, 4, and again this ethylene diamine which is there, that is being added, and then finally there is no aqua molecule, but the ethylene diamine molecule rise is also giving to a change in the color from pale blue, blue purple and violet colors as such. So this is how the color of the coordination compounds are being explained, and this is the strength of the ligands that has been generated. We had used this same theory in the VBT. Now here, how this is found out? See, in the VBT it was taken as a limitation, whereas here it is not a limitation. With practical analysis with respect to the octahedral splitting or tetrahedral splitting that has been seen, we are able to find that some of them are weak ligands, some of them are strong ligands, and this is how the overall order of ligands were given. It is something that we have to know, which was similar like the organic chemistry priority namings that we had. Now water is considered as a central ligand which differentiates between weak and strong ligands, and some strong ligands like carbonyl groups, cyanide groups, then ethylene diamine, ammonia, all these are considered strong, whereas if you see halogens generally are present as weak ligands in these cases. So what do these weak ligands do there is, the splitting offered by weak ligands is pretty much less, whereas the splitting offered by strong ligand will be high, and whenever there is weak ligand, magnetic properties will happen. Now the question is, after having studied this entire theory, could this theory explain each and everything of coordination compounds? Definitely some parts which were there were not explained exactly. Now, for example, if you see in the series there, the carbonyl group, EN group and all are shown to be pretty much strong ligands, whereas the halogens are shown to be weak ligands. Br minus, I minus, all these were termed as weak ligands, these were termed as strong ligands. Now, no doubt this was found out by practical analysis as such, but theoretically now we know that F minus indicates that fluorine electronic configuration 1s2, 2s2, 2p5, which indicates that this is inside, and these 7 electrons, 6 I have already shown as paired of electrons, the 7th one is here, and a negative charge indicates that they have excess, which means that negative systems are always excess in electrons, and when they are in excess they should be very much ready to give. Whereas if you take say something like ammonia and all, they have lone pair of electron which actually stabilizes it. But anions are those who have acquired an electron and they should be more ready to give away the electrons, which means that actually these should have been strong ligands, because having a negative charge indicates that they are excess of electrons. So when they are excess, they should have been strong ligands to give away, but when we see all the examples, we see that they are actually part of weak ligands. So this was not being able to explain theoretically by this crystal field theory. So let us see some of the limitations that are being proposed here in this crystal field theory. According to the assumptions of CFT, that the ligands are point charges. This was the first assumption that we had taken in the CFT postulate. Anionic ligands should exert greatest splitting effect, that I already explained now, where since it is negative systems, they should have been excess of electrons and they should have given more splitting, but that is not happening. So let us continue the point there. The anionic ligand should exert greatest splitting effect, but the anionic ligands actually are found at the low end of the spectrochemical series. So why are they weak ligands? Theoretically we could not explain. CFT does not take into account the covalent character bonding between the ligand and central metal ion. Now why it does not take into account is because whenever you show this metal and having 6 ligands in combo, it only believes that ligands give electrons to the central metal ion, and that is how we show this coordination bond like this. But we know very well that no bond can be 100% ionic, no bond can be 100% covalent as such. Here the factor of covalency was never taken into picture. So that is why that happens to be a limitation in this coordination compounds which is present. So with these limitations, they then took out further studies, which is ligand field theory and molecular orbital theory, which is actually out of the scope for our level at PUC. So we will stop the study of coordination compounds at crystal field theory itself, though we will study some other factors of it, but we are not going to study further theories at this PUC level. So I hope that you could understand this crystal field theory, which though at the outset looks a little complicated, but if you can understand the basic intricacies of orbitals, interaction of metals and ligands, this theory should be easy to analyze. So see you again with further segments of this chapter. Thank you. Sai Ram.